I am Ahmed Taha. I am going to present SVMax, a feature embedding organizer. SVMax promotes a uniform feature embedding. This is important for retrieval networks because the test classes are different from the training classes. So while it is better to promote class compactness for classification networks as shown on the left-hand side, it is important to spread features across many dimensions to fully utilize the expressive power of the feature embedding as shown on the right-hand side. In addition, SVMax organizes retrieval networks when they are susceptible to model collapse. Retrieval networks require intensive hyperparameter tuning to avoid model collapse and achieve state-of-the-art results. The intuition behind SVMax is simple. On the left-hand side, we show a feature embedding scattered over the 2D unit circle. In Figure A, the features are polarized across a single axis. The singular value of the principal horizontal axis is large, while the singular value of the secondary vertical axis is small. In B, the features spread uniformly across both dimensions. Both singular values are comparably large. Figure C depicts a PCA analysis using a 2D Gaussian dataset to demonstrate our intuition. The principal component in green has the highest eigenvalue, that is the axis with the highest variation, while the second axis in red has a smaller eigenvalue. Maximizing all eigenvalues promotes data dispersion across all dimensions, so we propose to maximize the mean singular value to regularize the feature embedding. We apply SVMax during training on the mini-batch embedding matrix E. We compute the singular value for the embedding matrix, then maximize the mean singular value. SVMax integrates with both supervised and unsupervised loss functions as follow, where LR is the original loss function, while lambda is a balancing hyperparameter. One caveat to this equation is the hyperparameter lambda. Tuning lambda can be difficult because the mean singular value depends on three factors: the range of the values inside the embedding matrix, the batch size, and the embedding dimension. Thus, every time you change the batch size or the embedding dimension, you have to tune lambda again. To address this problem, we constrain the embedding to lie on the unit circle, that is an L2 normalized embedding. This is a common assumption in retrieval networks. This provides lower and upper bounds on the mean singular value. The L2 normalization assumption allows us to impose bounds on the ranking losses as well. Once we assume an L2 normalized embedding, it is easy to compute lower and the upper bounds of the mean singular value as follow. Once the lower and upper bounds are computed, the final SVMax formula becomes as follow. The SVMax term takes the values from 1 to the natural exponent e. This fixed range makes tuning lambda easy because now it depends on the range of the original loss function. With an L2 normalized embedding, it is easy to compute both lower and upper bounds to ranking losses as well. This animation shows SVMax in action. We project the MINIST dataset on the 2D unit circle. We fix all training hyperparameters. We use a large learning rate to make contrastive loss struggles a bit. On the left-hand side, we show vanilla contrastive loss, while the right-hand side shows contrastive loss with SVMax. SVMax converges within a few epochs, while vanilla contrastive loss struggles to spread out. Since we know the bounds of both the ranking loss and SVMax, we set the lambda hyperparameter without grid search. I pick lambda such that SVMax never dominates the original loss function, for example 30% of the effective range of LR. In this figure, we evaluate SVMax against two baselines, the vanilla ranking loss and the spread out regularizer. We use 4 ranking losses: angular loss, impair, triplet loss, and contrastive loss. We do not tune the hyperparameter for a particular loss function. In this figure, we evaluate on CAP200 dataset. The y-axis denotes the retrieval recall at 1, while the x-axis denotes different learning rates. When the learning rate is too small, all methods are equivalent, but as the learning rate increases, vanilla ranking losses suffer. In contrast, SVMax remains resilient with large learning rates. In all previous experiments, we did not tune any hyperparameters. We just tried to deliver a fair comparison as much as possible. In this table, we evaluate SVMax with proxy anchor, a state-of-the-art baseline, using its own hyperparameter. SVMax delivers marginal improvement margins, if any. We evaluate SVMax using 2 different values of lambda to show SVMax stability. This figure shows the mean singular value during training. The blue line shows vanilla proxy anchor with a lambda equals 0. As you can see, vanilla proxy anchor automatically maximizes the mean singular value. The green and red lines shows the mean singular values with 2 different lambda. Lambda equal 0.1 pushes the mean singular value further towards the upper bound. A smaller lambda 10 to the power of -4 marginally maximizes the mean singular value and boosts performance relative to the vanilla proxy anchor. In conclusion, SVMax is a generic feature embedding regularizer. It supports supervised and unsupervised learning. The lower and upper bounds analysis makes tuning the lambda of SVMax easier.